Let us now get into the visualization module. Now what we are going to do over here is look at the effect of mesh, integration scheme, as well as the friction coefficient on the results in this particular problem. So I am going to create a Excel sheet. Each one of you must also be doing the same. So I'm creating a Google sheet labeled as parametric study for 3 roller beam bending problem, and then I'm going to run a series of simulations. For each simulation I'm going to record number of elements in thickness, number of elements in length, the integration scheme that we are going to use, friction coefficient, total degrees of freedom. So up till here are inputs, then total number of degrees of freedom, and from here on total number of degrees of freedom, total number of increments taken to solve the problem, CPU time for the problem, curvature of the rolled sheet, roller force and roll torque. These are going to be the outputs for the simulation. So for the first simulation I have set up, there are 2 elements in thickness direction, there are 100 elements along the length. The integration scheme is reduced integration. Friction coefficient was 0.4. Now in order to know about total degrees of freedom and total number of increments, let's go to the job module and let's go to monitor. Give it a second. Okay, now let's go to the data file. Now towards the end of the data file, okay, we can see that in this case the number of elements that user, meaning I have created, is 200. Total number of nodes defined by the user is 306. So even if you are having a student version of Abacus, you must be able to solve this problem. Total number of variables or degrees of freedom is 1815. So total degrees of freedom is 1815. The total number of increments taken to solve the problem is 912. The CPU time needed to solve this problem is, so that you can see at the end of the data file. So this is 279 seconds. 279 seconds. So it has taken about 5 minutes on my computer, which is MacBook Air, to solve the problem. Next we need to find the curvature in millimeters. Now to find the curvature, okay, we can use the following maths. So if the sheet that you are dealing with, if it bends into a section of constant curvature, then what would happen is, so you have the top layer, sorry, the top surface, bottom surface, neutral plane. Okay, so for any arc, okay, which is subtending an angle theta at the center of these circular arcs, then we have that radius of curvature for the neutral axis would be equal to t by 2 into si plus s naught plus si by s naught minus si, where s naught and si are the lengths of this any subtended angle arc. Okay, so we are going to use this particular formula in order to get the value of r. So alright, so let me just create another Google spread. Okay, so over here first I'll put the thickness is 5 millimeter. Okay, and then I have to get my s naught and si, and then I can write down the value of r over here. So let's do this. So I'll go to the results module, I'll go to the final deformed length. Okay, now okay, we are going to assume that planes normal to the neutral axis continue to remain as normal. So for s naught, query distance. So if I just take any element over here, the distance between these 2 points is going to be S0. So in this case, the deformed distance is 10.0209. So S0 is 10.0209, and SI is, so from here to here, is 9.98030. 9.98030. Okay, and R is equal to T by 2 into S0 plus SI divided by S0 minus SI. Okay, so R, radius of curvature in this case, is actually 1231.6 mm. So I'll take this as 1231.6 mm. Okay, now if you are in doubt as to whether or not this is actually the same everywhere, we could go to another point on the curve. Okay, so again, this is 10.0208, 10.0208, and SI is 9.98026, 9.98026. Okay, so this comes out to be 1233.4. so you can see that these are all very close by. So let me just round it off to the next highest integer. So 1232 is approximately the radius of curvature of the deformed sheet. Okay, now for the roller force, I go to tools, XY data, create ODB field output, continue, unique nodal, roll separating force, RF2, edit selection, select the point, done, plot. Okay, so this is the roll separating force. So as you can see, the rolling force is nearly constant once the once you are into step 2. So, and the roller force is close to 15 newtons, is close to 15 newtons. 1.5. Okay, now to get an more exact value, what you could do is you could save this. Okay, now once you have saved it, you can export it. So roller separating force, RF, export it to, so let's say in temp I'll call it as rf.dat. Okay, now once you have exported it, so let me go to that. So C colon temp rf.dat. Let me open this with Notepad. Okay, so I have this data. I could just copy this data, Control C, into, again I can copy it into a Google Sheet. Okay, now once I have copied it, what I can do then is I can go to step 2, and in step 2 I could pick some central portion. Okay, and then I could isolate it and take the average of this whole thing. Okay, So you can see that the average force is 15.9